Hello and welcome to my video on vertical circular motion. So when talking about vertical loops, we can describe centripetal force at any given moment as a sum of gravity and some other force. So before we really jump into these different examples, just keep in mind a few things. Okay, Fc equals F net. Okay, so at different portions of it, it will equal different things because it's F net. So if I talk about a situation where I'm holding a string, like literally this is my hand, okay, and I'm holding a string inside there, and the string is going out here to some sort of weight. Okay, now if I'm swinging that weight around in a circle, okay, that weight will be moving in a circle, okay, like this. Okay, moving around in a circle, you can kind of imagine that, hopefully. Okay, so now that that weight's moving around in a circle, there are different portions of the circle where there are going to be different amounts of forces. The big concept here is when we're talking about the minimum force, okay? You can have more force than this at any given moment, and we'll look at an example like that later, but at first, we're going to talk about the minimum force example, and then we can add to that whenever we want. So when it's on the top, do I have to pull down by any force to have a net force? No, actually gravity is pulling down, and that's all you need, right? Now let's skip and go to the bottom case. So now where the weight is down here. Now, gravity is pulling down by some amount of force, okay, the same force that it was pulling up at the top. But we have a force like this that is some sort of applied force. Now, if we're talking about a string, that's your Ft. And why is it so big? Well, because Ft minus Fg has to be at the bottom, right? That's what we have as our F net at the bottom. But at the top, our F net is simply Fg. So you can see how if we want to keep the F net the same, you actually need to pull up more when it's at the bottom. And two more kind of odd cases in here. Let's use blue for that. When we have the box on the left or on the right, the force of tension is the only force that is required. Now, there is a force of gravity that's kind of pulling down, but it lags behind, so we can kind of ignore it because it's not going in the vertical direction at all. So in these positions, F net equals Ft. In the top position, it equals Fg, and in the bottom, it's Ft minus Fg. So keep all of that in mind. Now, this is for minimum force. We could always add a force on top. So if we wanted to, we could add Ft here, or maybe I'll maybe call it something different. F applied here. We could add some extra force. We could add that same force if we add it everywhere. Then actually, your F net is going to be kind of the same, so plus, F applied. So you can have a bigger force if we add that F applied, or we can just talk about our minimum force, which is without that F applied, that extra force. Okay, but the big concept here is that F net is centripetal force, and it has to be the same the whole way through, otherwise we do not have the minimum centripetal acceleration. So when we talk about minimum centripetal acceleration, we're talking about this case up here. We're talking about when your Fc equals your Fg. Okay, now you guys are probably wondering, why do I have all these pictures of roller coasters here? This is the Mindbender from Galaxyland. Now that's been closed for a year or so, year and a half at this point maybe. And they've actually started to dismantle it during the summer, this last summer. But I do have some nice pictures here, and you can see that the Mindbender has a bunch of different loops. And this middle loop here is pretty much perfectly circular. Now, it's not perfectly circular because at the bottom it kind of comes apart. But all the way to here and all the way to here, it's almost perfectly circular. In fact, even these other loops are pretty close to circular. Most roller coasters are not. Now you can see here, this is an example from Disneyland. This one's not circular, but the top is circular enough that you can work with it. But most of them are not as circular as the Mindbender. Mindbender is very beautiful in that, because we can now do some calculations with it. So, neglecting friction, what is the minimum speed to go around the center loop of the Mindbender if the diameter is 10 meters? Now, let's actually zoom in, just give a little bit more clarity. Okay, the diameter is 10 meters, so the radius is 5 meters. Okay, very important. Okay, we also know FC, centripetal, is our F net, which equals your FG, because it's talking minimum speed, so it has to be FG. So our centripetal acceleration equals mg, which is our gravity, right? So now, if we're looking for the minimum speed, we can take that same formula and go mv squared over r equals mg. We're looking for the minimum speed, so we're going to solve for v. So we're going to move the m over and the r over. Those m's cancel, which is very nice, because now we can do square root of both sides and just have gr inside. Okay, so this is going to equal, and we're going to just go like this, square root of 9.81 times r, which is 5, and whoops, I didn't mean to press it twice, but there you go, which is going to be 7 basically meters per second. With 2 sig digs, so I guess better yet is 7.0 meters per second. Okay, so that's the minimum speed required. Now we're going to keep reading. Given the fact that the Mindbender has a top speed of 96 kilometers per hour, what is the biggest loop it could have done without falling off? So, actually, now I'm thinking about it, maybe that's incorrect. No, I think that should be fine. Okay, let's just try it out and see if this question makes any sense. So let's go with that top speed, right? So mv squared over r equals mg. Now we're going to solve for r. So r is going to move over. So m like this, v squared equals that. Now we're going to move the mg over, so it's going to be mv squared over mg equals r. Those m's cancel, so r equals v squared over g. So now we can solve for that by plugging in, oh, but we can't plug in 96. It's 96 kilometers per hour. So we need to multiply that by 1,000 meters per kilometer and divide by 3,600 seconds per hour. So really we're dividing by 3.6. So that'll be 96 divided by 3.6. So 26.66 repeating. 26.6 repeating meters per second. Now, the reason why I say this repeating instead of rounding it is because we're not at our final answer yet. So we need to plug that back into here, squared. So that's our velocity over our gravity, 9.81. And we get 72 meters, which is a massive loop, right? Massive, massive loop. In fact, it seems unbelievably massive. Well, no, just 2 sig digs, so meters. Well, the math checks out. So, not really sure why that's so big. It seems too big to me, but maybe let me know in the comments if you see a mistake here. I don't see it. But let's keep going anyway. We've got a couple other questions to try out. I think that is correct. Seems too big, but I think it's correct. Okay, in reality, the Mindbender was going around 75 kilometers per hour. So keep in mind that 96 is a top speed. Was probably not happening at the loop-de-loop. I'm making up these numbers now, the 75. Up till now, the numbers have been reality, roughly. I approximated the 10, but based off these pictures. In this reality here, I'm making up this number as 75. I assume it's slower. I don't know what speed it would have actually been going, so I don't know how many forces this is actually going to be. But let's try this out. What force would you experience as a rider if you weighed 60 kilograms? So now what's the force? So F net equals FC, which equals MAC, which is equal to M times your velocity squared over R. Okay, so our centripetal force, which is the force we're talking about here. But we also need to get 75 to be, this is kilometers per hour, right? So switching it into 20.83 meters per second. Okay, so now that you have that, now we can plug it back into this formula. So 60 times 20.83333 squared over R, which is 5. And so you experience 5,208 newtons, which we would write as 5.23 times, actually only 2 sig digs, times 10 to the 1, 2, 3 newtons. Alright, given the fact that we like to measure things in g-forces, comparing to fighter pilots, wow, I don't know how to spell, and spell check didn't catch it, I don't think that's right either. There you go. There you go. And such, how many G's would you experience on the Mindbender? Okay, so normally, how many G's do you experience? Well, normally you get mg, right? So in this example, that would be 60 kilograms times 9.81 meters per second squared. So in a normal case, 60 times 9.81, so about 600. Oh yeah, this is going to be nuts. 88.6 newtons, right? But in the Mindbender, we're saying that we get 5,200 newtons. Now it is only for a fraction of a second, but it is pretty quick. It is quite a bit. So how many G's are you experiencing? Well, this divided by 1 G tells you how many G's. So according to our math, which given this may be wrong, but you're experiencing 8.8 G's. I mean, it's possible. It was pretty crazy. Who knows, but it's possible. Okay, so that is somewhat realistic. I mean, it's a little bit high, but it is possible for a few seconds here. Here's one more example for you guys to try, and then that'll be the end of the video. So the Incredicoaster in Disneyland has a larger loop of around 20 meters in diameter. If you experience around 4 G's on the top of that loop, where it's actually circular, what is the speed going in? So I highly recommend that you pause the video now, try this out yourself, and see if you get the same answer as me. Okay, so if it is 20 meters diameter, just keep in mind that would be 10 meters radius. Okay, and we're talking about the top part of the thing, which is actually circular. So this part from here to here is actually circular. Just keep that in mind. That's what we're talking about. Okay, so what is the speed going in? So now basically so F net equals FC, which equals MAC, which equals keep in mind that we're getting 4 G's. So this equals mv squared over r, but this a here, we know this value now. Okay, so this is the big deal. So this is 4 times g, or 4 times 9.81. Okay, keep that in mind as we solve for v. We know that value. So now we're going to solve for v, so we're going to move the m over. So MAC over m. And we're going to move the r over, so the r will go up there, v squared. So the m's will cancel, so we'll have ACR equals v squared, which we can now get v equals the square root of ACR. Okay, so now that we have all that, we can plug this in. So 10 as a radius, and then times 4 times 9.81 meters per second squared, because it's 4 times a g. And this is going to give us a velocity. So 10 times 4 times 9.81 equals, and we're getting 19.839 meters per second. Now, this is meters per second. The question doesn't really tell us to do anything different, so you could simply just write 20 meters per second, and I wouldn't blame you if you stopped there. But let's get it into kilometers per hour, just to give you some idea of what that would look like. Actually, that times 3.6, and we get 71.4 kilometers per hour. All right, so I hope this video helped you better understand vertical circular motion, and yeah, good luck.